Significant figures, aka sigfigs, confuse a lot of students. Not because they're hard, but because they're often taught as a list of rules with no meaning. In this video, I will show you what significant figures actually represent, how to use them in addition, subtraction, multiplication, and division, how they work with log and natural log functions, and how to use them in mixed operation calculations. By the end, this should feel logical, not arbitrary. Significant figures tell us how precise a measurement is, not how big it is. For example, a mass of 2.0 grams is more precise than 2 grams. That extra zero matters. It tells us that the measurement was made carefully. So, significant figures reflect measurement uncertainty, not math skills. Now let's go through the basic sigfig rules. Rule number 1. Non-zero digits are always significant. Think about the number 123. There are 3 significant figures, 1, 2, and 3. Rule number 2. Zeros between non-zero digits are always significant. For example, 1002. There are 4 significant figures. Those 2 zeros sandwiched between the numbers 1 and 2 are significant zeros. Rule number 3. Leading zeros are not significant. For example, 0.0045. Only those 2 digits, 4 and 5, are significant. So there are only 2 significant figures. The leading zeros only locate the decimal point. That's their function. Rule number 4. Trailing zeros are significant if there is a decimal. For example, 2.50, 3 significant figures. 250 decimal, 3 significant figures. It is worth mentioning, however, that in scientific notation, the number of significant figures is determined only by the coefficient, that is, the number in front. The power of 10 has 0 effect on significant figures. Take an example of this number, 3.2 times 10 to the 4th. The coefficient here is 3.2, so there are 2 significant figures. Now let's discuss rule number 4 a bit more. Without a decimal point, trailing zeros are ambiguous. What exactly am I talking about? Let's take an example of the number 1500. 1500 could represent 1.5 times 10 to the 3rd, so there are 2 significant figures. 1.50 times 10 to the 3rd, so there are 3 significant figures. 1.500 times 10 to the 3rd, 4 significant figures. All 3 represent the same value, that is 1500, but very different levels of measurement precision. So, without a decimal point, we simply don't know which one is intended. Okay, so let's talk about addition and subtraction first. For addition and subtraction, significant figures depend on number of decimal places, not on total digits. I have seen students making that mistake often. So what's the rule? The rule is your final answer can only be as precise as the least precise decimal place. For example, 12.11 plus 18.0 plus 1.013, put the whole addition into your calculator and get the result out. The calculator will give you 31.123. Now you have to look at the decimal places of the individual numbers. 12.11 has 2 decimal places. 18.0 has 1 decimal place. and 1.013 has 3 decimal places. So the least precise decimal place is 1 decimal place. And we have to round the answer to 1 decimal place. That means we are going to get 31.1. Okay, so let's talk a little bit about rounding. This part follows standard rounding rules, but it is important to apply them after we have identified the correct level of precision. What is the basic rounding rule? You have to look at the digit immediately to the right of the last digit you are allowed to keep. If that digit is between 0 and 4, round down. If that digit is between 5 and 9, round up. So let's go back to the previous example. 12.11 plus 18.0 plus 1.013. Calculator gives you the result as 31.123. Now you know that you can only keep 1 decimal place based on the rules, so you have to look at the next digit right to the last digit you are allowed to keep, that is 1, and that is 2. So 2 is between 0 and 4, so you have to round down. So your final answer would be 31.1. All right, so now let's talk about multiplication and division. For multiplication and division, significant figures depend on the number of significant figures, not on decimals. The rule says your answer must have the same number of sigfigs as the value with the fewest sigfigs. So take an example, 2.5 times 3.42. Plug these two numbers into your calculator, multiply them, you'll get an answer as 8.55. Now, you have to check. 2.5 has 2 sigfigs. 3.42 has 3 sigfigs. So your final answer must have 2 sigfigs. So you have to stop after 8.5. And then look at the digit right next to 5. In that case, the digit is 5. So you have to round up, not round down. So your final answer is going to be 8.6. Now remember, always round at the very end, never during the intermediate steps. Now let's talk about exact numbers for just a little bit. Exact numbers have infinite number of significant figures. Some of the examples would include counting numbers, like there are 3 test tubes or 5 students in this class, things like that. Anything that you can count, those are exact numbers. And there are also some defined numbers, like 1 kg is 1,000 grams, or 1 inch is exactly 2.54 centimeters. Things like that. These are also exact numbers. Exact numbers do not limit significant figures in calculations. We will talk about exact numbers in a different video, so keep an eye out for it. Our next discussion is on significant figures in logarithm and natural logarithm. Now, this part is often skipped, but this is important. So what's the rule? The rule says the number of decimal places in the result or in the answer equals the number of sigfigs in the original number. So for example, log of 2.45. Now if you put that into your calculator, you will see there is an answer of 0.389166 something. Okay, so now the number of 2.45 has 3 significant figures. So your result must have 3 decimal places. So in this case, you have to round down and your answer will be 0.389. Take another example, natural log of 1.32. 1.32 has 3 significant figures, so your answer must have 3 decimal places. So plug that into your calculator. The calculator will give you a number like 0.27763 something. So you have to have 3 decimal places. So you have to stop after 0.277. Um, so the next number to the 7 is 6. So in this case, you have to round up, and your final answer is going to be 0.278. Now, this rule comes from how logarithms compress numerical uncertainty. For an anti-logarithm, the number of sigfigs in the answer or in the result equals the number of decimal places in the exponent. This is exactly the reverse of the natural log rule. Let's take a few examples. Example number 1, base 10 antilog, 10 to the 2.34. Now, plug that into your calculator. The calculator will probably give you an answer like 2.18776 times 10 to the second. Again, understand this, the exponent 2.34 has 2 decimal places, so the result can only have 2 significant figures. So that 2.18776 times 10 squared will now become 2.2 times 10 squared after rounding up. Example number 2, natural antilog, e to the 1.256. Same thing. Plug it into your calculator. The calculator will probably give you something like 3.511347967, something like that. But the exponent 1.256 has 3 decimal places, so your result can only have 3 significant figures. So in this case, you have to round down. Your final answer will be 3.51. Now, one type of calculation that becomes really important in chemistry in this regard is pH calculations. Or if pH calculation is given, the calculation of hydrogen ion or proton concentration. Now, if you guys recall, pH is defined as negative logarithm of hydrogen ion or proton concentration. So let's take an example of pH being equal to 3.45. And the question is asking you to calculate the concentration of hydrogen ion or proton. Now, in this case, pH has 2 decimal places, so the concentration of H plus, that result must have 2 significant figures. So again, plug that into your calculator, 10 to the negative 3.45. It will give you something like 3.548133 times 10 to the negative fourth, something of that sort. But you can only have 2 significant figures, so this should be correctly reported as 3.5 times 10 to the negative fourth. This is why pH decimal places matter so much in chemistry. Okay, so the final section is about mixed operation calculations. When a calculation involves more than one operation, like addition, subtraction, multiplication, or division, any combination of these, we need to follow something that is called PEMDAS, which is an abbreviation for parentheses, then exponents, then multiplication, division, then addition, subtraction. And of course, we do have to follow significant figure rules. So let's break it down step by step. Number 1, follow PEMDAS. Do parentheses operation first, then exponent, then multiplication, division, then addition, subtraction. Do not round intermediate results yet. Step number 2, determine the allowed precision for each step. Remember, addition, subtraction results are limited by number of fewest decimal places, whereas multiplication division results are limited by number of the fewest sigfigs. So one thing to consider, even though you know the precision of each step, do not round yet. This prevents accumulation of rounding errors. And that leads to step number 3. round only the final answer after all steps are complete. Let's take some examples. Example number 1. In parentheses, 12.11 plus 18.0, parentheses closed, times 2.3. According to PEMDAS, parentheses operation has to be done first. So 12.11 plus 18.0, the result will be 30.11, but you are only allowed one decimal place. So if that makes you comfortable, underline the first one in that number, 30.11. This will give you a signal how many digits you are allowed to keep in your first operation. Then do the next operation, which is multiplication. Do not round 30.11 yet. So now you're multiplying 30.11 times 2.3. This will give you 69.253 on your calculator. Or if you could do it by yourself, that's even better. But 2.3 has two significant figures, whereas your first operation, 30.1, remember you underlined that one, that had three significant figures altogether. This is how many digits you were allowed to keep, but you didn't round at that stage. So 3 significant figures versus 2 significant figures, you are allowed to keep 2 significant figures in your final answer. So in this case, 69 is how many digits you are allowed to keep. Look at the next digit right to 9, that's 2, so you have to round down. So your final answer is going to be 69. Example number 2, a little bit different order. 12.11 plus, in parentheses, 18.0 times 2.3 parentheses closed. So in this case, the operation inside the parentheses, again, according to PEMDAS, will be your first operation. 18.0 times 2.3. Your calculator will give you a number of 41.4. But understand this, you are only allowed 2 sigfigs because it's multiplication, and 2.3 has the fewest number of sigfigs. So again, if it makes you comfortable, underline the 1 of 41.4. This will give you a signal in your next operation how many digits you're allowed to keep in the first operation. So now let's move to the next operation. 12.11 plus 41.4. Again, recognize I did not round 41.4 yet. So 12.11 plus 41.4, put it in your calculator or do it in your head. It's going to be equal to 53.51. But again, in the first operation, you are allowed to keep 2 sigfigs. In the final operation of addition, understand this, 12.11 has 2 decimals, but that 41.4, you were only allowed to keep up to 41. Remember that? So 41 doesn't have any decimal place. So your final answer cannot have any decimal place either. So you are allowed to keep up to 53, and then you have to look at the digit right to 3. And in this case, the digit is 5, so you have to round up. So your final answer is going to be 54. Okay, so some common mistakes. Let's clear them up. Do not round too early. Always keep extra digits until the final steps. Number 2, confusing decimal places with sigfigs. Remember, addition, subtraction, decimal places. Multiplication, division, sigfigs. And number 3, forgetting log rules. Significant figures control decimal places, not total digits. In closing, significant figures aren't about being picky. They're about honesty in your measurements. Once you see them as a way to communicate uncertainty, the rules stop feeling random and start making sense. If this helped, like the video, comment, subscribe, and I'll see you in the next one.